You've been listening to the Sartorial Marsh Night theme from Xenoblade Chronicles Definitive Edition. Hey everyone, welcome to this week's recitation. That song, as I just mentioned, was actually a recommendation from the form I sent out in the announcement today, though it is music I quite like. I'm not going to pretend that I'm not just going to kind of pick a lot of songs I like from that list, or be like unbiased or anything, but definitely feel free to submit songs to that, and I will try to pick at least from those lists instead of the songs I would otherwise choose, because there has definitely been a lot of good recommendations so far. I might have to put a couple together and have them loop, although for a 15-minute slot it doesn't really do that much. Regardless, welcome to this week's recitation. We're going to be covering some some of the remaining tree stuff that I didn't get to last week, and then we'll have some time for exam review related stuff. So, with that said, let's get to this, get myself set up. Your normal announcements, your current homework, homework 4, your BST homework, that's not going to be due until the 21st. You've got quite a while to work on that, but definitely if you haven't started that by now, I recommend at this point after you finish the exam, you should probably go ahead and get started on that. And the big reason behind that is because this Friday, we're actually going to release homework 5. That's going to be your Heaps homework, which we've been talking about in lecture for quite a while. We're going to start talking about a bit in recitation today, and also next week we will talk about it in much more detail. It's not that difficult of a homework. It's mainly implementing 2 methods, although those 2 methods can be a little difficult for some people, so I wouldn't recommend doing it last minute. But if you want the full amount of time to work on it, you should try to start your homework 4 on the earlier side so that you have more time for homework 5. The big thing is that your exam 1 is tomorrow. You've got a window between 6 a.m. and midnight Eastern Daylight Time. That's the current time zone in Atlanta, Georgia, or New York, depending on what standard you like to use. That's the window to take it. Once you start the exam, you'll have 60 minutes to complete it. We estimate it'll take about 50 to complete it, but you've got the extra 10 minutes because the online format can get a little bit weird. That time can't go past this midnight, so if you start the exam after 11 p.m., you're going to be real sad. And because of the scratch paper upload, if you start the exam after 10:45, you're probably also going to be really sad. So this window is a little misleading. It should really only go till, in your mind, it should really only go till 10:45 or so. You should make sure you start the exam before then. This isn't... Okay, cool. Sorry. Other things, with exam 1, you saw in the announcement we sent out this morning, we are going to be closing down Piazza and office hours for the day of the exam. Thursday, office hours will still be closed because we'll be grading the exam, but Piazza will be back open, although TAs won't really be on it very much. Generally, we try to get all of the exams graded in one day on that Thursday, so hopefully with any luck we'll get them all graded, and early next week we can have your grades back to you. But we'll see. You will probably get some updates on that. Some exams take longer than others. Other stuff, we've already put out the, or I believe we've already put out the worksheet for the this week's recitation on Canvas. Practice exam answers, I'm sorry I didn't get those on Sunday night, but they are published on the Canvas files section now. I see a question about the scratch paper. So the scratch paper upload is a lot of questions about scratch paper. The scratch paper upload is a separate assignment from the exam. The scratch paper upload does not have honor lock enabled. You will finish the exam, turn in the exam, end the honor lock session, then open up the second assignment, which is just like a regular Canvas assignment. And once you do that, then you will upload your scratch paper to that assignment. In between, before you open that assignment, you can actually email it to yourself or take the pictures or whatever. That's not important. I do think the scratch paper assignment has a 15-minute time limit, so don't open that window if you think it's going to take you a while. Another question, I think TAs will get to that question, but yeah, so the scratch paper, that's a separate assignment. Honor lock's not on that. Please don't try to take pictures of your exam during the actual exam assignment on Canvas. If you have technical issues on the exam, please look at the email, look at that announcement we sent out this morning. We document exactly what you should do, exactly who you should email. That'll be emailing Dr. HB or Dr. Moss and CCing both myself and Landon. All of our emails are in that announcement. Piazza is closed, you will not be able to make a question on there. Alright, today we're going to be talking about the BST traversals. It's the one thing I didn't do last week, even though we did it first in lecture. The reason for that is because I wanted to cover pointer reinforcement first. That way you guys could start on your homework if you wanted to, especially because these are much simpler, as you'll see. Then we have some time for exam review, and then if there's still time after that, we will do a very brief introduction to heaps, like not even starting on the operations, just basically an introduction of what heaps are. So prepare if you have things that you want to ask about for like exam review topics. You should get those prepared. Skip lists are not on the exam. They're not on the topic list. There's a topic list. I've answered that a lot of times. I'm sorry. I'm a little sorry. So for exam review, make sure if you have questions for those, I'd say wait. Don't ask them right now. Don't wait till we get through the BST traversal stuff. I have kind of a dedicated time when I'll be going over an easier thing where you should then start asking those questions and I can start going through them. But don't flood the Q&A right now before we start with the traversal stuff. With that said, let's go ahead and get started today. Our first topic is going to be Bsg Traversals. I know this page is a little lengthy with the amount of stuff on it, but it is definitely the longest page I have today, so it shouldn't be that bad after this. So why do we want to do these Bsg traversals? Well, it's the same reason we might want to do a traversal on any data structure. If you think of like a linked list, it's possible we might want to, for instance, just print out all of the data in our linked list. And with something that's linear like that, it's really easy just to iterate through it, and at every single index you print something out. But with a BST traversal, with a BST, it's not quite as simple because we're not looking at a linear data structure. Everything is just kind of in a weird tree way, and we don't know exactly like how, like maybe you can figure out a way how to print it out, but now the order matters. So what ways can we print it out in an order that makes sense? And that's why I have this particular order here, because we're going to have multiple different ways that all traverse the tree, all are going to print out all the data, but the order is going to be the different part, and that's what's going to differentiate them. There's two main categories of traversals, depth and breadth. We'll talk about depth first and then get to breadth later. The depth traversals are all recursive. Also, sometimes you'll see this called like DFS for depth first search versus like BFS for breadth first search, but those are more of just because later in the course we'll talk about other things where those terms make a lot more sense. It's just if you ever hear like DFS or BFS, this is kind of what we're talking about. So depth traversals are all recursive. The basic idea is it's going to kind of like go as deep as we possibly can through the tree, and then once we hit like leaves or something, then we're going to kind of back our way back up the tree and repeat the whole process. There's three main steps that are going to be common in every single depth traversal. A step that I'm going to call C is kind of writing the data at the node we're currently on. That might be usually like adding it to a list or printing it out to the console. L, which is going to be recursing to the left, so these are all recursive methods, so we can call them on a different node. And R, which is likewise going to be recursing to the right. And the order we do these three steps in is going to determine which traversal we're doing. The first traversal is a pre-order traversal. These order the steps as CLR, so mark the data, then recurse to the left, then, and by then, when I say then, I mean after the whole recursal to the left is done, then we recurse to the right. So this is kind of like a top-down traversal, so this is going to mark a parent's nodes before we go on to its children. The focus is really bad today. I thought I fixed that earlier. I can try to see if I can make it a little better. But this is going to be like a top-down traversal, so we're essentially going to be visiting some parent node before we visit the children node. It's because this was on. Okay. I have to turn that setting off every single time. Sorry, I forgot. So this is going to be like top-down traversal. We add the parents, then we add the children. I think I've said that 3 times. The order that we get out of a pre-order traversal is very important, because if we added the data in that exact same order that we get from this traversal, we would produce an identical tree to the one we started with. So another unique quality of this means for every pre-order traversal, there's only one BST that matches up exactly with it. Which is nice, because in-order traversals don't have that property. In-order traversals, which go left, then mark the data, then go to the right, the name suggests this, it's just going to get the data in order, in sorted order. Obviously, this is for a BST. I should specify that. You can do these traversals on just an arbitrary binary tree, but these qualities don't all necessarily hold. The top down and bottom up still do, but the whole adding and sorted order, that obviously doesn't have meaning if you're not working with a binary search tree. So in-order traversals, unlike pre-order, there can be multiple trees corresponding with any in-order traversal. If you just think of like taking one tree and looking at like a balanced version of that tree versus a degenerate version of that tree, those would have the same data, which would print in the same order. So no matter how our tree looks like, in order will get it in sorted order. Finally, there is a post-order traversal where we go left, then right, then mark the current node. This is a bottom-up traversal. So pre-order was top-down, we hit parents, then children. Post-order, before we visit a node, we're always going to visit all of its children. So we don't get to any node before the entire subtrees beneath it are visited. Another useful thing about this that sometimes we talk about in this class is if you removed the data in the same order that you get back from a post-order traversal, then every single removal you'd be doing is a leaf node removal, because we visit all of a node's children before visiting it itself. So by the time we get to a node, we've gone past all of its children. If we removed them all of those would have been leaf removals. That's not as useful of a quality. This bottom-up idea is a little more important. You'll talk about these traversals all a bit more in other courses. So you'll probably see them again, and you'll see a bit more about relationships between pre-order and post-order traversals and how those can be used. Also, because I did mention it for pre-order, post-order traversals also do uniquely identify BSTs. So for every post-order traversal, there's only one BST that can produce it. So these are the three depth-first traversals. All of these are going to be the recursive ones. You have to, on your homework, it's basically going to be each of these being like 4 or 5 lines, almost identical, just with the lines in a different order. Make sure on your homework, when you inevitably copy-paste to write these methods, that you actually change which recursive method you're calling. That's very important. Also, as a note, make sure that you're not creating your list in every single recursive call, because allocating that space is inefficient. Just like you have the dummy node that you pass into every single recursive call in the remove method, in these depth-first traversals, you can create the list in the public method and pass it in as a parameter to every single recursive call. I lost points for that on my homework, so now you know so that you won't lose points on yours. Now let's talk about the alternative traversal, and we'll do examples of all of these on the next page, so don't worry about that. The opposite of a depth-first traversal is going to be a breadth traversal, or breadth-first search, breadth-first traversal, all the same. And we only have one breadth traversal that we talk about for trees, and that's going to be a level order traversal. This is not a recursive traversal, as opposed to depth traversals, which are. How breadth traversal is going to work, how level order will work, is we will visit nodes in essentially frontiers based on the number of edges from the root. So we visit the root, then we visit all the nodes kind of 1 away from the root, then 2 away from the root, etc., etc. I see some questions, more questions about honor lock. If you have technical issues, you're not going to be able to send us emails until after your exam is closed, but we do get to see like a log of how you go through the exam, so we can accurately assess things even if you're not in the middle of the exam at the time. TA can repeat what I said earlier about the lists. All right, I'll give you guys a couple more seconds to finish writing this down or take pictures of it. The next page has a little bit more information on level order traversal, so leave some space below this if you're going to continue trying to put everything in one spot. Also, again, I think I say this every week, but huge thank you to all of the TAs helping me answer these questions in the Q&A. I would definitely get very sidetracked and lose a lot of time if I answered every single one of them out loud. So thank you to all of you guys. Huge help. All right, let's go ahead and move on. And by move on, I mean continue on level order, just on a different page. Make sure all this is in frame. So level order, how we actually do level order, because I haven't explained that yet, is we're going to use a queue. So depth first traversals did everything recursively. And if you remember, recursion works very much like a stack. Level order is going to use a queue. Now this is just like a regular queue, like you can use a linked list in Java. That's the most common implementation. Some people like to use an array deck because that implements queue, obviously. But any choice you want to use on your homework is fine, provided that it implements the queue interface or can do these operations effectively. And how it works is we add the root first, then every iteration, this is an iterative process, not a recursive one, we remove a node from the queue, we're going to write its data to the list, and then enqueue both of its children. And that process is going to give us that breadth traversal I described earlier, where we get everything kind of level by level. And we'll see an example of like how that looks, but this is kind of the way that you're going to write it. We've done examples of that in lecture 2. All of these traversals in terms of efficiency are really simple. We have to visit every single node in our tree. There's no way around that, so all of them are just going to be O of n traversals. As a note, we're only visiting every node once, because once we visit a node and kind of finish our process on that node, we move on to different things. We're never coming back to where we used to be we're never coming back to where we used to be after we finish a recursive call. So we're just getting it to every node, which means that it's very simply just going to be an O of n operation. There's no like best, worst, average case about it. Always O of n. Now I'm going to talk about something that we tend to call the T method. I've also seen it called like the Euclidean Tor before. This isn't a coding strategy. This is entirely a strategy for diagramming questions or for like writing things out on your own that makes doing these traversals very easy. All you need to do is take every node, draw these 3 little spokes to the side of it. This left one represents pre-order traversals, the right one represents post-order traversals, this bottom one represents in-order traversals. Then we're going to do an outline of the whole tree, and every time we hit one of the spokes, we're going to record the data. And where we record the data depends on which spoke we hit. Now, how do we outline the tree? Well, let's do an example of that. Trying not to take anything off screen here. So you always start from the root, kind of on the left side, and you start going around. So here we hit this first spoke. That's the left spoke for 50, so we add it to the pre-order. We continue going. Oop, that didn't draw. We hit the left spoke for 25. We hit the left spoke for 10. Now after we get there, we come around the node. Here we hit the bottom spoke for 10, so it gets added to the in-order traversal. Come back up. The right spoke adds it to our post-order. Here. Now we add 25 to in-order. And 25 to post-order. Now we come around, we hit this bottom spoke and add 50 to in-order. We come around like that. We get 100. Going to go a little faster now. We get 75. Now here we get 75 in in-order. 75 in post-order. 100 in in-order. 125 in pre-order. 110 in pre-order. 110 in in-order. And in post-order. Then 125 in both. Then we start coming back up and we hit 100 in post-order. And finally, kind of missed, but 50. Now we look at these traversals. We can look at our in-order traversal and see that we did get all of the data in order. We look at our pre-order traversals. You see that we're kind of visiting nodes before their children. So we visited 50 before 25. we visited 100 before all of the nodes below it, etc. Versus post order, we visited the children of a node before the parent, so we visited everything before the root, and you see we visited 75, 125, and 110. We visited all three of those before we visited 100. So they're kind of opposite in some ways, but you'll notice they're not like reversed order or anything. So this is a really nice way to diagram these traversals and make everything really easy to do on a piece of paper. Obviously, like in code, you can't replicate this strategy because you can't like draw lines around in your code. But this is still very useful for like exam questions, or if you're just trying to look at a tree and determine something based on it. Level order, I guess I can do a quick example, right, what it would be over here. So level order is kind of a different strategy. We're going to go level by level. I'm going to kind of like mutilate this graph a little bit, so if you want to get a picture of how this traversal looks, I'll give you a couple seconds to do that now. But we're basically going to go through each level from left to right and add the data that's on every single level as we hit it. So we start by going through this first level, and we hit 50. Then we're going to go through the second level, and we're going to hit 25 and 100. Then we're going to go through this third level, add 10, 75, and 125. And then finally we'd go through this last level and add 110. Skip list will not be on the exam. I can draw arrows on some of these so you can see where things are going. So, level order traversal, very easy to do just by looking at it. You just go level by level and write the data in order from left to right. Pretty straightforward. I'll give you a couple more seconds if you want to finish writing stuff down, finish working stuff out, or get your pictures. And then we will start doing a minor review topic, and I'll let you guys start getting your questions ready for exam review. All right. I have the advantage that today I remembered to actually fill up my water bottle, so I'm not going to start having a dry throat halfway through recitation. All right, my camera got quite a bit tilted. All right, so this is mostly going to be like a little review topic for you guys. Hopefully you guys will have, hopefully you guys will have seen most of this before or understand a lot of this. This is kind of the opportunity if you start having questions about what you want me to talk about during my exam review section. This is when you can start kind of getting those questions ready and asking them, because I don't imagine there will be a ton of questions on this section. So let's talk a little bit about reference versus value equality, because it's come up a few times on the homework and we really haven't gotten a chance to talk about it. In Java, there's two main ways that we can compare objects. We can compare objects using this double equals sign, so that's equals equals, or we can use the dot equals method. Now, double equals will check if two variables represent the exact same location in memory. So, no matter how similar two objects may be, if they're not literally representing the exact same variable in memory, this would return false. The alternative is dot equals, which will take two objects and check if they're logically equivalent to each other. Now, what does logically equivalent mean? Well, every class has to implement some equals method, and that equals method is what's going to determine what that means. For people, maybe it says, okay, if their name is the same, then their date of birth is the same, then they're the same person, basically. It's a very simple version, but close enough. If a class doesn't implement this equals method, Java's just going to use object's default equals method, which is essentially just double equals. So even if in the worst case where your object doesn't implement this method, this dot equals will still work, and it would be the same as doing double equals anyway. On the homework, you can always assume that we have a properly implemented equals method for the generic type that we give you and are working with. In general in this class, unless you are checking if an object is null, you should probably use the equals method. There will be rare few times in this homework where you actually want to use double equals for some object. Dot equals is almost always what you want. The two exceptions, the one I just mentioned, if you're checking if an object is null, you don't want to use dot equals because you run the risk of having a null pointer exception, because trying to do like null dot equals something is a null pointer exception. And also primitives, simply because primitives don't have a dot equals method. You have to use double equals. There just isn't even a choice. So, some quick examples of how these two works. We have these 4 dog classes here, or dog objects here, and these 6 statements. So, we create a new dog Jack. Dog 2 is just equal to dog 1. Dog 3 is also a new dog named Jack, and dog 4 is a new dog named Buzz. Now, let's see how these 6 statements evaluate. So dog 1 double equals dog 2. If we look at these two, dog 2 is just an alias for dog 1. So this one is going to be true. They actually do represent the same place in memory. Likewise, if double equals is true, obviously dot equals is also going to be true. They're logically equivalent and memory equivalent. Now dog 1 equals dog 3. These are 2 dogs with the same name. Now we're going to assume that the dot equals method here checks if 2 dogs have the same name. But double equals between these 2 things, because they're not literally the same thing in memory, this one is going to return false. As a comparison, dog 1 dot equals dog 3, that's going to return true. It checks what their names are. In this case, they're both Jack, so it's going to return true. And if we try to compare like dog 1 and dog 4, obviously they're different dogs, so both of these are going to return false. The important ones in this example were these 2 over here. That if I didn't use the dot equals method, then 2 objects that should have been the same wouldn't have been treated as being equal. So this is why we tell you to generally use the dot equals method in your code, because it's going to prevent weird situations like this where you don't find that things are equal that actually should have been. On your homework, we do test for this. You're not going to lose all the points if it's wrong, because we've advanced past that stage in our testing, but you will lose quite a bit of points if you use this double equals everywhere instead of dot equals where appropriate. Alright, oh god. I'll give you guys a couple more seconds, and then I will start looking through some of the questions you guys asked, and I'll try to explain things a bit in the time I have with the abilities I have. Alright, so let's do some exam review. First, I will mention that we have actually created a little Kahoot. Unfortunately, there's no real way to run a Kahoot over this recitation just because there's way too much time delay going on. But you can still look at these questions. You can look at the answers we've set to them. It might be a little hard to read that. That's tinyurl.com/1332 exam1 review. So pretty straightforward URL name. I can also put it out in an announcement. I have that ability. One second. I can be fancy here. There we go. So now you guys can just click that link. Sorry if you're going to be confused when that link appears a couple seconds before I actually said it. But that will have some useful questions for you. But otherwise, I'm going to go and start looking at some of the things you guys have mentioned. I saw one person say, is it possible for me to demonstrate a BST, presumably that's what they meant, not the K-pop group, BST remove root and down heap during the exam review. So I'm not going to do the down heap because heaps aren't on this exam, and I want to try to keep this as exam 1 topics. So let's do a BST remove from root and see how that goes. Let's give myself a little BST here. So the nice thing with BSTs is, at least from like a diagramming perspective, there's no real difference between removing from the root and just removing from any arbitrary other node in the tree. Nothing's particularly special. I need to pull this up so I can see what I'm doing. So let's remove root. So remove 50. And let's say we're using predecessor, because that's how I set it up to be more difficult. So when we do a removal with a predecessor, remember that our first step is to find the data that we're trying to remove. Done. Then our second step is to actually find where the predecessor is. So remember, finding the predecessor is very easy. We start by going one step to the left, then we go as far right as we can without hitting null. So 40, 48, and then we stop because we can't go right anymore. Even though there's a left child, we stop at 48. Then we're going to copy 48's data into the root. So now instead of a 50 here, this is a 48. I'm not going, since this is like a diagramming example, I'm not going to write out like storing the data in dummy nodes. This is just going to be how it looks like. If you want examples of pseudocode or how it works in code, there's plenty of that in this Recitation video, or like pseudocode slides, or just straight up in the visualization tool. So we copy the predecessor's data into the root, into the node we're trying to remove, and then we want to remove this entire node. Now, to remove a node with one child, all we have to do is look at its parent, and that pointer just needs to point to whatever this one child was. It's going to be just like that. And the reason this works, and the reason this is nice, is whenever we're removing the predecessor, that's guaranteed to be a one-child remove case. Because if 48 had a right child, that node would have been the predecessor instead. Because remember, we kept going right until we hit a node with no right child. So these predecessor removes are always going to be one-child removes. So we can just set this parent pointer to be this single child. And there could be more nodes below this. Those don't matter. This process works anyway. With pointer reinforcement, this is really easy to accomplish, which is nice for the sake of your homework. So now just to redraw what this tree looks like, 48's up here. Nothing to the right of it changed. And then here we have these 3 nodes. This is still a valid BST. It's always nice to check after you're done if the BST you ended with is still valid. But everything here is still good, and we've successfully removed the root using predecessor. Again, I don't really want to do a down heap or remove example because that's not going to be on the exam. We'll talk about heap operations a lot next week too. Pointer reinforcement also, because that is a BST coding technique essentially, you shouldn't expect it to show up on the exam. It's not really anything that you're going to have to deal with. But definitely get some practice with it in your homework code, because something like that is definitely fair game to show up on exam 2. Compare Iterable and Iterator. So Rena's already done a great job of answering that question, but I can just talk about it a little bit more. Iterable is a quality of, like, for example, a data structure or something we might want to iterate over. The iterator is the object that's actually doing the hard work, doing the iterating. It's kind of that behind the scenes person walking through the data structure and giving you all the data in it. So iterable is something that data structures implement. Iterator is something that an inner class might implement, for example. I'm peeking my mic a little bit. 1 second. Hopefully that helps. What might be examples of diagramming problems other than Bsg traversals on the exam? Again, look at some of the recitation worksheets we've given. We could give you like diagramming things with decks, diagramming things with like array lists, with linked lists. There's definitely a lot of other examples we could give. How well will you need to know the comparable interface? So comparable interface wouldn't really apply on exam 1 stuff because the only things we've talked about that are comparable are things that go in a BST or things that go in a heap, and neither of those two coding topics are showing up on exam 1. For the test, do you need to use dot equals? You should know the difference between dot equals and double equals and use the appropriate one. So in general, that will be dot equals, but you might have times where you want to use double equals. Accessing at a known index of an array is O of 1. So pre-order and something I said, pre-order and post-order traversals both uniquely identify a BST. That means if I give you a pre-order traversal and tell you it's a pre-order traversal, you can construct the exact tree I used to generate it. The same thing with post-order traversal, but again, those traversals aren't necessarily the same. As you saw in the other example we did, these two traversals are definitely not the same. They're not even like backwards of each other or anything. They're completely different traversals, but both of those traversals uniquely refer to this tree. If I had a different tree here, I guarantee you I would have gotten a different pre- and post-order traversal, even if I might have gotten the same in-order traversal. Rena answered that one already. So would it be possible for me to write a table with all of the big O for each ADT and data structure? So there's a lot of those. I'm not going to be able to write down every single one. People have started compiling some decent ones on Piazza, and there's definitely been some good answers. I think there's a blank big O sheet under the Canvas files under one of the extension resources. It's like the 6th one from the top. And feel free to ask any specific questions to TAs and we can answer them. Heaps aren't on the exam list just because we started writing the exam before covering heaps and decided not to put it on it. If a node in a BST has no children, it is a leaf node with height 0. Predecessor and successor are only applicable if a node has 2 children. If you are removing a node with 1 child, you should not even think about predecessor or successor. You should just do the simple 1-child removal like we did here and move on with your life. Can we do a couple, what would be the best data structure questions? So I don't know if I'm going to be able to like give you specific questions, but I can maybe give some examples. Just try to think about like the qualities of what make a data structure good, and try to think about when we give a problem, we're going to try to kind of list some of these specific qualities. So we might, in our scenario, it might involve a situation where the things you always need to access are always the most recently things you would have added to your data structure. And that's going to work something like a stack, because stacks have that last in, first out structure, where the things we pull out of the stack are the last things that we just put into them. Versus like a queue, if you see something that says like, okay, we have these things we're inserting and we want to get them back in the same order we put them in, that might be a queue. For arrays versus array lists, remember that arrays don't have to be contiguous. We're allowed to have these blank spots, but array lists work nicer if we might have to resize, if we don't know exactly the size of input that we're going to be using. But arrays and array lists are both nice if we might need to index into some random spot in the middle. So try to not think about like, here's this very specific situation, here's this data structure that fits that situation. Like, oh man, if I'm using a music playlist, I want this specific kind of linked list. Try to think about, okay, if I have a playlist where I want to be able to move back and forth, and I want after I reach the very end, I want to go back to the beginning, those qualities appear in a circular, doubly linked list. Or something like that. So try to think about it in terms of specific characteristics, not specific examples. So BST, remember that most of our operations were in general O of log n average case versus O of n worst case, because on average we have a balanced BST and we only need to kind of go down one branch to complete our operation. But Rena's done a good job of answering that question in a little more detail. What would I say is the hardest topic on the exam? That is very different by people. A lot of people usually struggle on some of the multiple choice questions, so those might be questions like scenario matching questions or Big O questions. Usually it's like a couple of those questions are really hard and everyone struggles with them, and a bunch of the questions are really easy and like 97% of people get them. But what questions are difficult depend on each specific person. Harneet's done a good job of answering why removing from the back of a circular singly linked list is O of n, because we need to access that second to last node. We can't do anything without that reference. Someone asked, if I have an iterator, but that collection of objects does not implement iterable, can I still use the iterator to traverse to that collection? So iterators, like specific iterator instances, are specific to a current instance of a data structure. So what I mean is, I don't just have, when I make an iterator object, that object isn't like, so for a linked list, let's say I have a linked list. Let's say I have the class, and then here I have my list is going to be a linked list. So this is a specific instance. This is the class. So this class has the method to generate an iterator. But we're only going to call that from this instance of the method. So we would do like mylist.iterator. And then we get back an iterator that is specific to this exact instance of the list. So it can iterate through the current items that are in my list at the moment I create it. If I try to add or remove things while I'm iterating, everything might break, so don't do that. So it's not really possible for you to have an iterator for a collection that isn't iterable, because there'd be no way to get it. Hopefully that answers your question a little bit better. That scrolled up my Q&A for some reason. Recitation worksheets are in the campus or online canvas, not the recitation canvas, under the recitation worksheets, like recitation/worksheets folder. When I said BST operations on the topic list, I mean like add, remove, and search. So like exactly what I did over here, this is a kind of operation you might have to do on the exam. There's no coding of BSTs because you haven't even finished your homework. A lot of questions about like iterators and iterables. That question's been answered a ton of times on Piazza and by TAs at this point. You're not going to have to like code a specific iterator class, but you might want, it might be possible in your code that you want to do a for each loop, which kind of implicitly uses an iterator, but you don't really need to use them explicitly. A really common question that comes up is why is like searching for in a BST not best case O of 1? So best case is a little weird. We don't really like to talk about best case a lot with data structures because it doesn't really mean very much. You'll see that when we start talking about algorithms in this course, it will be really obvious why we have this best case efficiency, because sometimes algorithms have a really nice best case. But data structures don't usually have something analogous to that. It's usually these weird edge cases for some combination of how your data structure looks and what operation you're doing. And at that point, that doesn't even really relate to your operation anymore. So saying like, oh, BST search is best case O of 1 because you can search for the root, that doesn't really mean anything, and it's not really useful to anyone trying to look at a BST's operations. So we try to say, okay, best case for a BST is it's a perfectly balanced tree. And if it's a perfectly balanced tree, then search is never going to take more than O of log n time. And that analysis is a lot more useful to us when we're looking at data structures. But we don't generally even like asking about best case efficiencies for data structures because something like that doesn't really matter. If we are looking at a sorted array list, we can search in O of log n time using binary search. But otherwise, in an unsorted array list, you have to do a linear search through every single element, which takes O of n time. There are some Piazza questions about... Okay. These are the same question. Okay. Rena's answered a very good question about the accessing index 2 of a singly linked list of size 4 or more. Remember that when we talk about big O, that is talking about the growth of operations as the size of our the size of our data structure changes. So if we're doing some very specific operation, that's always going to be the exact same number of steps, regardless of how big our data structure is, then that's a constant time operation. Even if it's not one step, if it's a constant number of steps invariant to the size of our data structure, that's still O of 1. Can I give an example of using a list number to create a tree by pre-order? So, Rena mentioned using the CS tool is a very good way. Again, CS tool, that is an official thing by us. That was made by a TA, a former TA, and is still updated by current TAs. That is going to generally be exactly the same as how we do stuff in class. But when I say making a tree from these pre-order traversals, I'm literally saying call add on every single element one after the other with your normal add method. That's all it means. It's nothing fancy. Predecessor or successor is an implementation detail. You're never really going to know which is better or worse to use. You generally just pick one for your implementation and stick with it. On your homework, we specify exactly which one you want to do. Questions will always specify whether you should be using predecessor or successor to do the removals. That way we know exactly what answer to expect from you. You should understand what the difference between full, complete, balanced trees are. I wouldn't expect to see what is this tree balanced on this exam, because balanced we talk about a lot later with AVLs, but you should definitely know complete and full trees at the very least. All of your code for the exam has to be in Java. If you write code in a language that's not Java, we're not going to like you very much. And that should be a fate worse than failure. Mild sarcasm, if it's not obvious. BST Unorder Traversal is a sorted list. Remove from back of a circular singly linked list is really similar to how you would do it on a regular singly linked list. You iterate to the second to last element and do something like this node dot next equals, in this case, head, because you're removing the last node, but this node dot next equals this node dot next dot next. Can I remove 50 using the successor method? You can pull that up on your Viz tool, but I can also run through an example of that. So let's redraw out that tree. This one's going to be a much simpler example because I really wrote this for a predecessor example. So we're removing 50. We want the successor. So predecessor says go left once, then all the way right. Successor says go right once, then all the way left. So left from here, there's nowhere else I can go. So 60 is my successor. So what I do is I replace the node in the root with 60, and then I want to remove 60. And again, one child removes, all I do is I set this right pointer to 75, and I get the tree 60, 75, 25, 40, 48, 45. That's a 5. So much simpler example. That's why I did predecessor on the other example. AVL is an AVL a normal binary tree. An AVL is a subset of BSTs, which always stay balanced. We will talk about that 2 or 3 weeks from now. It is not required to complete all the reality checks until October 24th, although we highly recommend doing the ones that are relevant to this section of the class. Recitation worksheet answers are not posted, but you can always make posts on Piazza or go to office hours, although it's a little late for that to ask about them. Coding questions. the ones that we have on practice exams are probably the closest. Sometimes reality checks we ask like really challenging questions on. Sometimes we ask like really easy questions on. So it's kind of hard to say like those are good examples. But the practice exams usually have good ones. Format and type of the exam are very similar to the practice exam. Check style does not matter for the coding questions as long as you have like proper line breaks and you have like proper curly braces and your code's like invalid Java. That's fine. We don't care that much about style guides, but try to make sure your code is invalid Java. Mild syntax errors aren't going to be that bad. Oh, did Neha post this? I think Neha might have actually posted the recitation worksheet answers recently. I don't know if we put an announcement about that, though. I will... Yes, worksheet answers are there now. Sorry about that. So, recitation worksheets are there now, in the same folder as the actual worksheets. Sorry about that. That's important. But yeah, like random things like, oh no, you're missing like some random semicolon. That's not like a huge deduction. I don't even know if we deduct for a random missing semicolon. Check style or syntax errors that actually make it more difficult to understand what your code is doing, you might lose like half a point to a point for. It's not the biggest deal in the world. We want to see that you understand the algorithms and you can at least code them in basic Java, not that you can flawlessly write code in some random canvas text box that's not designed for writing code. Grant gave a really good example on like time versus space complexity. Right now we haven't really talked about space complexity yet because we haven't talked about any structures that use like varying amounts of space. It'll come up later when we talk about skip lists. Rena's also given a good example on depth versus height of a tree. Depth is kind of a measure of how far down from the root you are, versus height is a measure of how far up from a leaf you are. And there's ways to calculate them. Can I explain the definition of a balanced tree again? If I take any two children and I compare the heights of those specific nodes or those specific subtrees, then the heights of them, when I say children, I mean any two siblings. If I compare the heights of those nodes, then those heights don't differ by more than 1. So like this node has height 1, this node has height 2. Those are exactly 1 off. So this tree is overall balanced. You'd have to check that for every single node. But you'll mainly see that later once we start talking about AVLs. Lectures, the B section lectures and the C section lectures are both recorded and uploaded. If you go on the modules page to the HB/MOS lecture information page, you can see all of the lecture videos. For coding question, yes, you should include brackets. If you don't include curly braces, that can create some ambiguity in how your code executes, and that can potentially cause you to lose points because not having brackets can legitimately change how your code works. So please include those. It also helps us auto-format everything so we can actually read it and grade it in a reasonable amount of time. Neural networks are definitely not binary trees, I would say, but they are subsets of trees because they don't really have cycles usually. I think in general they're at very least a subset of graphs. Not really a topic for this course. Depth of a root is 0. So access from a linked list in general is not O of 1. The whole point is if I say, okay, write me a method called getSecond that always gets the second piece of data in a linked list, that method is going to be O of 1 because it's very specific and it doesn't change no matter how the linked list is. If I write a method that's like get to give me an index and I'll get you that index of the linked list, that operation does scale with how big the linked list is. So that's going to be O of n. But stuff like getting the first node and getting the last node, those will usually be O of 1, assuming you have a tail. After you submit your entire exam, you obviously can't go back, but you should be able to freely move back and forth between questions as you wish. We have it set up so that you're allowed to go back, even though you only see one question at a time. Code is all entirely graded by hand. We give partial credit for, like, if you miss some random edge case, you'll still get partial credit. There's no feasible way for us to auto grade your code because We're not going to like give you a 0 for some random syntax error. You'll be able to see the rubric for exactly how we grade your code. Recitation worksheet answers are the same place of the location. Someone posted a Big O guide that's apparently pretty useful. You should be able to go to previous questions. As far as I know, that's how it's set up. I will check that setting later to make absolutely sure, but that's how it's supposed to be set up. How many spaces do you need for indentation? You don't need any. The standard is 4, unless you're like some other weird things, like some things use 2 spaces. GitHub's like, let's use a random amount of spaces that's not 4. That's not important though for the exam. You don't really need to indent them. The height of a root with no children is 0 because it's also a leaf node, and leaf nodes have height 0. So if this is my tree, this has height 0, and this node has depth 0. Big O guide, someone linked that in the Q&A. You can find it there. That's not like an official thing though. We will explicitly tell you if you should be considering any exceptions. Very often we tell you to ignore them, but sometimes we do say, like in the Java docs, like we have those throws tags that you should pay attention to. Always follow the Java docs, always read the instructions. So, okay, about this facial recognition feature, if someone can show me where it is or like where to look at it, I looked at all the settings for Unlock. There is no setting called facial recognition. There is no setting that even seems like it would be close to facial recognition. I have scratch paper enabled, so that presumably works. But as far as I can tell, this doesn't seem to be a setting I can turn on or turn off. I don't see any way I can change any setting released to that. If it's on, I'm really sorry, but that's kind of out of our control. It seemed to be like a relatively new feature that didn't go over well. It's possible that the feature isn't enabled on this exam because I might have created the exam with Honor Lock before that feature got added. That might be why I don't see it anywhere. But there's nothing really I can do about it now. All right. Wasn't there some operation we discussed that has an n log n time complexity? The bad method of build heap that we talked about, so not build heap, but just adding everything to a heap one by one is n log n. Your constructor for BSTs that takes in a collection is also average case n log n. You are allowed 2 pieces, like 2 pages front and back, so like these 2 pieces of paper for your scratch paper on the exam. They should be blank. They don't need to be like printer paper. They can be like lined paper. They can be graph paper, but 2 blank pieces of paper. If a coding question doesn't specify an error, then you shouldn't throw it. You should only throw exceptions that we specify. Very happy I brought my water bottle. Right. If there's... The questions are starting to slow down a bit, so I might start talking about heaps for a bit, but otherwise I'll keep answering questions. How would the time complexities be different from an unsorted list as an array and a sorted list? The only real difference would be if you're searching. If you're searching through a sorted list, you can use binary search to do it in O of log n time. If you're searching through an unsorted list, you could you have to linearly brute force every single element, which takes O of n time. Also, adding things in a sorted list can potentially be a little bit different because you need to find the correct spot for it, but that's still O of n, so it's not really going to be any different from an unsorted list, although you won't really have those nice O of 1 complexities most of the time. Do you have to write front and back and show both sheets of the scratch paper to the camera? So you don't need to write. I don't think we care if you really write front and back on them, but you should show both pieces of scratch paper to the camera, like during the room scan section. Do it in such a way that we can very easily tell that you're like those are 2 different pieces of paper. That way you don't need to write anything on them. I think we do want you to write down like front and back on them before you upload them, though. You're welcome, random person, anonymous student. If you're not sure about a portion of our code and we add a comment detailing what we would have done, will it get points? We only grade you off of code you've written. Comments never receive points. The only time where a comment would ever affect your grade is if you've accidentally written ambiguous code. So like you forgot a curly brace that, like this is literally only if you forget to write a curly brace that is seriously important, and your code in your comments make it very clear exactly where that curly brace was supposed to go, then we can definitely give you points for that instead of having to worry about the ambiguity. Although we tend to give students the benefit of the doubt in cases like that. But you will never get points for comments that are not actual code. If your code doesn't work, a comment will not redeem it. The questions seem to have slowed down quite a bit. So I will continue answering those as they pop up, but I'm going to start talking a little bit about heaps. And when I say a little bit, I do definitely mean a little bit. We're not going to go very far today. Alright, so what is a heap? Heap is going to be the next type of tree we talk about. Will you have to write pseudocode? No, we will only ever ask you to write actual Java code. Sorry, I'm going to kind of be going back and forth between the Q&A questions and this, so I apologize if it gets a little distracting, but I will try to keep those answers. Don't forget, you can always check the actual Q&A to see the TA answers. So heaps, what we use them for is they are data structures that can keep track of either the largest or a smallest value in some set of values. That's going to be the main point we want them. So how we accomplish this is with a tree that has these specific shape and order properties. The shape property is that we're dealing with a complete binary tree. So remember, complete means that our tree is filled in for every single level from top to bottom, except for that very last level, which is filled in from left to right with no gaps. So that means we don't have like random nodes on the right or nodes in the middle. Everything starts from the left on that bottom level of the tree. Then we have this order property. The order property of a heap, we've got kind of two different versions of a heap, a min heap or a max heap. For a min heap, the parent is always going to be smaller than both children. For the max heap, a parent is always going to be larger than both children. That relationship is only between the parent and the children. There's no explicit relationship between the two siblings. So one could be, the right could be smaller than the left, the right could be larger than the left, it doesn't matter. We only care about this ordering relationship between the parent and the children. A very important note is that heaps are not BSTs. In fact, there is very little overlap between trees that are heaps and trees that are BSTs. It's basically only size 1 trees and some size 2 trees can be both. So they are different things. All of our operations that we do when we're working with a heap, we're going to fix this shape property first. We're going to maintain that complete shape, and then afterwards we're going to fix our order property, because the shape property is a lot harder to maintain. So that's going to be our priority. Would the lengths of coding assignments be similar to ones in the 2018 practice test, like a method or two, or is it fair game to for a question to ask you to write out an entire class for a data structure? It would definitely be more similar to the 2018 practice exam. There might be some things where we ask you to write out like a lot of methods, because those methods are like 2 lines each. But we're not going to say like write your entire Arraylist class, because that would just take way too long. You don't have a ton of time on these exams. We're not going to give you questions that will take like half an hour to write, or just rely on you memorizing every single line of code you've written. I read something about how DFS traversals use stacks and BFS traversals use queues. That is correct. So remember, our depth traversals all were recursive. Remember that recursive things operate using a stack for the recursion, versus a breadth first traversal, we used a queue. And when I say queue, I mean like a literal queue. We can instantiate like a linked list which implements java.util.queue and use that for our breadth first traversal. You'll see later in this class we'll talk about BFS and DFS in a lot more detail, and you'll see the differences between them and how stacks versus queues work. You'll also learn about them in approximately 4 to 5 other classes after 1332, so just in case you don't learn them now, you'll definitely learn them then. I guess that depends on what your threads are, but pointer reinforcement is not that important to know for this exam because BST coding won't be on it, and homework 1 through 3 coding doesn't involve pointer reinforcement. Alright, I think you guys have had a decent amount of time to write this down or take a picture of it. It's not really that much, it's just kind of a very basic introduction to heaps. So let's talk a little bit about how we actually implement these. Should our creation of a new BST given a collection to copy over be n log n, or is there a more efficient way to do it? It's actually going to be n log n in the average or best case. In the worst case, it could actually be O of n squared. But yeah, there isn't a better way to do it. We fully expect you to just call your add method n times. It's heaps that are going to have the better way to do the construction, but we're not going to talk about that until next week. So how do we implement heaps? Well, BSTs were trees, heaps were trees, so you think we might implement them the same way, but that's actually not correct. BSTs used nodes and pointers to implement all of our tree functions, but heaps are actually going to use arrays, and there's a couple of reasons for this. A big one is because we're dealing with a complete tree, it means there's no gaps in the array. So if we tried to create an array to represent a BST, it would have a ton of gaps where all of like the nodes that we're missing would be, versus heaps, nice and complete, nice and contiguous, works very well with an array. Also, it's going to make going from a node to its parent and children very easy. With BSTs, we use these pointers to go from parents to children, but we didn't really have any way to go from children to its parent. Now, obviously, we could have added in a new pointer to do that, but then that's using extra memory, because now nodes have to store even more things. Versus heaps, with no pointers at all, we're going to be able to go from nodes to their children or nodes to their parents super easily. How we do that is with some simple math. If we leave index 0 of our array empty, and this seems a little weird, Rena is correct about my threads on theory intelligence with a robotics minor. If we leave index 0 of the heap empty, I'll get back to this in a second, then for some node or piece of data, could really be either, so some node or data, because we're not really storing nodes, we're just storing individual data pieces. If it's at index I, its parent is at I over 2, its left child is at I times 2, and its right child is at I times 2 plus 1. Super simple math, especially because if you're familiar with some binary operators, division and multiplication by 2 is a really quick operation to do. So you'll see these can be really fast. So why do we leave index 0 empty? Well, A, it makes us these operations really easy to do because it's just these 3 very simple calculations. If we didn't leave index 0 empty, you'd be like a random +1 and -1 in all of these numbers, and that just makes our operations a little slower, it makes our math a little complicated, and for the 1 extra spot of memory we gain back, it's really just not worth the effort. So we leave index 0 empty and start adding our data starting at index 1. So our heap would look something like this. We'd have like these elements go in, this empty, this index we always leave empty, sometimes we put an X through it. When I say leave empty, I mean we basically put like null there. Some of our spots at the end might not be filled in yet if our heap isn't completely filled to capacity, but we start at index 1 and have it contiguous from there. And again, I mentioned this earlier, a big advantage of this implementation compared to like nodes is we use less memory compared to like all of the nodes and pointers involved. We can implement it either iteratively or recursively. We have options on your homework, you're allowed to do either. And later, when we talk about a new nice and cool algorithm called build heap, arrays are going to make doing build heap really easy, versus you wouldn't really be able to accomplish that if we weren't using an array. We're not going to talk about build heap until next week, even though we did talk about it a little bit in lecture on Monday. The one operation I am going to talk about today is access. Now, heaps are designed to keep track of the smallest element or the largest element. We only care about accessing that element. We don't care about anything else. And that element is going to be at the root, which is index 1. The smallest element of a min heap is at the root. The largest element of a max heap is at the root. That's just inherent. It follows the properties I talked about on the previous page with our order. And since these pieces of data are always at index 1, and we have an array where we can access index 1 in O of 1 time, this access operation is really easy, O of 1, super fast, nothing else to it. So next week we'll talk about add, remove, and probably build heap, maybe even talk a little bit about skip lists depending on what our schedule is. I haven't looked at that recently. But otherwise, those are the main questions I have. If you guys have questions about heap stuff, I can answer those quickly. Otherwise, with the couple minutes we have left, I can do my, I guess at this point it's a weekly card trick, and then we'll end things off. Thank you very much for all of the kind words that we've gotten. I know I've heard a couple TAs mention that they heard very kind things in office hours. We've tried to be very active on Piazza and helping you guys prepare for these exams. But thank you guys a lot for all the kind words. It really does mean a lot to us. Don't forget to extend that out to your other classes as well. TAs and instructors love to hear students like actually express their gratitude when they feel it. It really helps us. So don't forget for your other classes too, not just 1332. Alright, everyone's definitely had time to write that down by now. So let's do a quick card trick. I've got my deck right here. This is a deck I actually got in Seattle because it looked super cool and I wanted to get it. If I'm correct, this actually may be the very first card trick I ever performed with this deck. So you guys are getting to see something new. With these cool like dragon aces. I just couldn't resist this, I'm sorry. So, new deck, you can take a look. It's not in like any particular order or anything. Also, new decks make doing this spread super easy. So it's not just like a ton of practice. You can, pretty much anyone can do that with a new deck. And the cards I'm going to get, if you can't tell already, is I'm getting the 4 aces out. Because that's what this trick is going to involve. Look at that. It's a beautiful ace. So these are our 4 aces. And that's what I'm going to be using for this trick. So we've got ace of diamonds, ace of clubs, ace of hearts, and ace of spades. The fanciest ace, that's where most of our... That's what most people usually tend to focus on because it has the cool design and stuff. And what we're going to be doing in this trick is we're going to be taking these aces and one by one we're going to be flipping them upside down. So, obviously I need to do it in a slightly more impressive way than that. And how I'm going to do that is just with a little wiggle of the cards. I can magically flip one of the aces upside down. Now you see the ace of diamonds is face up. So I need to do that for the other aces. Start with everything face down, give the cards a little wiggle, and now magically the ace of clubs is face up. Move on to the next ace, start with everything face down, give the cards a little wiggle, and now magically the ace of hearts is face up. Now finally I need to do the ace of spades. This is usually the hardest one, but I'll give the cards a little wiggle, and now suddenly the ace of spades is face up. So we've got all 4 aces that I've each turned face up one at a time, but now for the finale of the trick, start with everything face down. This time I gotta give the cards a big wiggle. I'm gonna set them on top of the deck, cut them into the middle, and now just give a little turn, and just like that, let's see if I can do a nice spread on here. You can see that all 4 aces have been turned up at the same time. That is the trick. You can look it up. It is called the French aces, I believe. It's on A Million Card Tricks channel. I will probably link it in next week's announcement. But hopefully you guys enjoyed. Hopefully you guys have had a fun recitation. This is going to be the end of it. And I will see you guys next week. Good luck on your exam.